Okay, here's a couple problems I want to look at. Okay, so this picture here, I have an astronaut. Okay, so they're doing a spacewalk. Here's a space station. Okay, here's the astronaut. They've just fixed a satellite out here. Okay, so here's the astronaut over here. Okay, they just got done fixing a satellite with a wrench. There's the wrench. And now let's say they're at rest, okay, with respect to the space station and the satellite, and they need to get back to the space station. Okay, now they can't move their arms like they're swimming, right? Because there's nothing to push off of in space. So, how can they get back to the space station? Well, one way they can do that is they can throw the wrench. Okay, so what I did is I drew the astronaut holding the wrench. Okay, this is the before picture. Here's the after picture. So before picture, they're not moving, initial velocity is 0. The after picture, astronaut, she throws the wrench to the right. Astronaut is going to recoil backward, okay, to conserve momentum. So looking at that picture, okay, so this is my system, astronaut and the wrench, okay. So there's no net external forces on the system. There's no third object, third mass that comes into the system. So the system's closed and isolated. So initial momentum is equal to the final momentum for the system. Momentum is conserved. So initial momentum 0, because nothing's moving. Initial momentum 0. Final momentum is I have two things. I have the astronaut, right? So P final is I have P final astronaut plus P final for the wrench. Okay, so I wrote that P final for the astronaut, P final for the wrench. Remember, momentum is mv. Okay, so there's P final for the astronaut, P final for the wrench. So if I calculate the final velocity of the astronaut, I have a huge mass of the astronaut in the denominator. The mass of the wrench is small. Okay, so small numerator, large denominator. That would make this a very small number. Okay, so the astronaut's going to recoil with a slow speed, but it's negative, which means the astronaut is going to recoil back to the left. Okay, now obviously the astronauts out here, okay, they're not going to throw the wrench because the wrench is expensive, and you don't want that stuff flying around in space. So how does the astronaut get back to the space station? How the astronaut gets back to the space station, obviously, they don't throw the wrench, okay? They have a little pack on the back, okay? And what gets ejected are little wrenches, okay? But actually not little wrenches, but mass. So instead of little wrenches of mass m, okay, the stuff that comes out is just gas. So this stuff is compressed, okay? So that gets ejected one way, and that will have the astronaut recoil back that direction. And then by adjusting the direction of the nozzle, okay, astronaut can turn around and then make their way back to the space station. Okay, another problem. All right, so here I have rain falling on a roof. Okay, so I have raindrop falling on a roof. All right, so let's say this is the rate at which the rain falls. It falls at 0.06 kilograms per second. Here's a coordinate system I picked. So let's say the rain hits the roof going at 15 meters per second. I just picked a number. Okay, 15 meters per second. It sounds kind of fast, but I'm just going to work at that number. So it hits the roof and the rain comes to rest on the roof. All right. So I want to find the force exerted on the rain by the car. I didn't want to use R for rain and R for roof, so I'm using car. So this is the force exerted on the rain by the car. So Newton's second law, okay, trying to find the force. So force is change in momentum with respect to time. Okay, so it's the change in momentum of the rain because the roof exerts a force, okay, exerts an impulse. It exerts a force to change the momentum of the rain, to stop it. So I did P final minus P initial, okay, there's my delta T on the bottom. So V final of the rain is 0, okay, and I have minus mv0 over delta T. Well, m delta T, whoops, that's that. That's the rate at which the rain falls. So I have that number, okay? V0, that's the initial velocity of the rain, and I chose downward as negative. There's positive, there's negative. Okay, so that goes in as minus 15. Okay, that's the rate at which the rain falls. So that gives me 0.9 newtons, and it's positive, so that means it's upward. So in that picture, okay, this force here, that one right there, that's the upward force that the roof has to exert to stop the rain. So that'd be like there's your hand, okay, someone drops a ball, okay, the ball hits your hand, you would have to exert that big upward purple force to stop the ball. So the roof has to do the same thing. It has to exert a large upward force, that one, to stop the rain. Okay. Now, that's the force exerted by the roof on the rain. Now I want to find the force exerted on the car's roof by the rain. Okay, this is the force exerted on the rain by the roof. Now I want to find the force exerted on the car by the rain. So the car exerts an upward force on the rain. Newton's third law says the rain exerts an equal and opposite downward force back on the car. So the force exerted on the car by the roof is minus the force exerted on the rain by the car. Hope I said that right. So the force exerted on the car by the rain is equal and opposite to the force exerted on the rain by the car. So it's minus that number. Okay? And it's negative, so it points downward. So in this picture up here, the roof exerts that upward force, and due to the negative sign, the rain exerts that downward force. That's my 0.9, my minus 0.9 newtons. So the rain exerts 0.9 newtons of force on the roof of the car. Okay. Now let's say it gets cold and the rain freezes. Okay. So now you have hail falling at the same rate. Okay. Let's say the hail falls at the same speed. Okay. But the difference between what the hail does and what the rain does, okay, is the rain hits the roof and stops. Okay. The hail hits the roof and it bounces. So it comes in with a certain speed and it goes out with a certain speed. So let's say it comes in with a speed of 15, goes out with a speed of 5. I'm just making that number up. Okay. So I want to find the force exerted on the hail by the car. Okay. So the roof of the car has to exert a force to stop the hail. All right. All right. So I'm going to find that. So Newton's second law. So change of momentum of the hail. So P final minus P initial. Factored out the M. Okay. But mass per time, that's the rate at which the hail falls. I have that number. And I have the same coordinate system. So it comes in with initial velocity of minus 15. Okay, because my coordinate system minus is down. Initial velocity, final velocity, it goes out with a final velocity of 5. Okay, so I have 5 minus a minus 15. I put that in. Okay, and so this gives me the force exerted on the hail by the car's roof to stop it is 0.12 newtons. That is positive, so that's my purple upward force. That's that one. Okay, so the car's roof exerts a force in that direction. Okay, now it's bigger. Okay, up here, the force exerted on the rain by the car only had to exert a force of 0.9 newtons. Here, the car has to exert a force of 1.2 newtons on the hail. Okay, now why is it bigger? Let's see. Well, we want to now find the force exerted on the car by the hail. Okay, this is the force exerted on the hail by the car. We want the force exerted on the car by the hail. Okay, so we want to find the force exerted on the car by the hail. Well, that's just equal to minus the force exerted on the hail by the car. Okay, this we already have. That's right there. That's my 1.2 newtons. Okay, and that is right force exerted on the hail by the car. That's plus 1.2 newtons. I have a minus sign there. Okay, so the force exerted on the car by the hail is downward. The minus sign says it's downward. So I drew that force over here. Okay, so the downward, right, it's minus. Okay, minus means that it's downward. All right, so what the the rain only exerted a force. Where's the rain? The rain only exerted a force of 0.9 newtons on the roof of the car. The hail exerts a force of 1.2 newtons on the roof of the car. Okay, so why does the hail exert a bigger force on the roof than the rain does? Okay, and that's because the roof has to exert a bigger force back on the hail than it has to exert back on the rain. And the reason is with the rain, all the roof of the car has to do is catch the rain. Okay, here with the hail, the roof of the car has to do two things. Not only does it have to catch the hail, okay, and bring it to rest, like it does the rain, okay, it then has to throw it back upwards, okay, with that final speed. All right. So think of this as if you were on a skateboard and someone threw like a bowling ball toward you, okay, you would catch it and then recoil back. But if someone threw the same ball and you caught it and recoiled back, and then you threw it back to them, you would then keep recoiling back more. Okay, so not only does this roof up here have to catch the hail, like it does the rain, it has to throw it back. So it has to exert that greater extra force, 1.2 newtons, okay, as compared to 0.9 newtons, has to exert a greater force to stop it and throw it back up than it does for the rain. So, okay, so there's your frozen rain. Okay, there's your big hailstone. Okay, makes a big mess. Okay, that's not good. All right, and then I have a video that shows large hailstones bouncing.
Well, I figured it would. I said I'm not surprised there aren't more windows busted. That was amazing.